today's video, we're going to look at the relationship between the H plus ion concentration and the OH minus ion concentration in aqueous solutions, and we're going to introduce the concept of pH, something you may have heard about before. Now you're going to understand what it means. It turns out that in any aqueous solution, in other words, in any solution that's made with water as the solvent, the concentration of H plus times the concentration of OH minus in moles per liter will always multiply together to give you the same number. It's 1.00 times 10 to the negative 14th. This has a name. This number is so important. It's called the water dissociation constant, and it's abbreviated kW. Now in pure water, just like in any aqueous solution, the concentration of H plus times the concentration of OH minus, 1 times 10 to the minus 14th. Water, in fact, acts as an acid and a base, but not to a very great extent. It's an extremely weak acid and an extremely weak base, shown here by the double-headed arrow. But if you think about what happens if you had some water and it were to split up, stoichiometrically, HOH, when it breaks up, would have to give you exactly as many OH minuses as H pluses. The stoichiometry is 1 to 1. So if I started out with some random number of water molecules and no H plus and no OH minus, and I let this dissociate or ionize, I would lose some number of moles of H2O. I'm not sure how many, so I'm just going to say X. But however many moles of H2O I lose, I have to gain exactly that number of moles of H plus because it's 1 to 1. And I have to gain that number of moles of OH minus also. So by the time it stops ionizing and I've reached that dynamic equilibrium where the back and forth reactions are going at the same speed, I have X moles of H plus per liter and X moles of OH minus. So the concentration of H plus in pure water times the concentration of OH minus in pure water, according to the stoichiometry, would be X squared, whatever X is. But here's something I know. X squared has to be equal to kW. In other words, it has to be equal to 1.00 times 10 to the negative 14th. So that means X is equal to the square root of 1.00 times 10 to the negative 14th, and that is 1.00 times 10 to the negative 7th. So that's equal to the concentration of H plus in pure water, and also it's equal to the concentration of OH minus in pure water, or in any aqueous solution. Now, since kW is equal to the concentration of H plus times OH minus, I can develop a way to solve for H plus if I know OH minus, and vice versa. The concentration of H plus would be given by kW divided by concentration of OH minus. If I divided both sides by H plus, I'd find this. Concentration of OH minus is equal to kW divided by concentration of H plus. And of course, kW is that magic number, 1.00 times 10 to the negative 14th. So here's an example problem. In seawater, H plus concentration is 5 times 10 to the minus 9th. What is OH minus concentration? Well, OH minus concentration is equal to kW divided by H plus concentration. So plugging in our numbers, for kW we put 1.00 times 10 to the negative 14th. And for our H plus concentration in seawater, it's 5 times 10 to the negative 9th. The number that we get to one significant figure is 2 times 10 to the negative 6th, and that's equal to the OH minus concentration. You try this one. Stop the video and see if you can calculate the H plus concentration in household ammonia, which has an OH minus concentration of 2 times 10 to the negative 3rd. Well, here's your solution. We know that H plus concentration is equal to kW divided by concentration of OH minus. So that's 1.00 times 10 to the negative 14th divided by 2.0 times 10 to the negative 3rd. The answer turns out to be 5.0 times 10 to the negative 12th. Now we're going to start to talk about pH, but before we do that, you might need a little math refresher. We're going to define what logarithms are. The logarithm of a number is the number to which you must raise 10 to get that number. Now that's really confusing, so let's try and work it out through an example. Let's say I wanted to know what is the logarithm of 10 to the 6th. Well, the logarithm of a number is that number to which you must raise 10 to get that number. So the logarithm of 10 to the 6th is 6. I have to raise 10 to the 6th power to get 10 to the 6th. So the logarithm of 10 to the 6th is 6. So work out these two examples. Stop the video and give me the logarithms of these two numbers, and I'll give you answers to confirm. To get 10 to the 2, we have to raise 10 to the 2. So the logarithm of 10 to the 2 is just 2. The logarithm of 10 to the negative 14th would be negative 14. Now those had mantisses that were equal to 1. In fact, they weren't even written. And that's easy. You can use your calculator when the mantissa isn't equal to 1, and it will give you the logarithm. So let's use our calculator to work out these two examples. I'm using a TI-83 calculator, and most TI calculators will work the same, and lots of scientific calculators will be very similar to this. I'm going to just push the log button, and then I'll enter 2 times 10 to the negative 7. Hit enter, and I get negative 6.69. I would round this off to negative 6.7. Let's do the next example. Log of 2.3 times 10 to the 4th, 4.361727, but I would write this as 4.36. The significant figures rule, which I'm not expecting you to memorize, but I just want you to be aware of it, is the number of digits that are in the number you're taking a log of, that's the number of decimal places that are in the log. So I have 1 sig fig in 2 times 10 to the minus 7th. That means I will have 1 decimal place in 6.7. 2 significant figures here. That means 2 decimal places after I take the log. Why is that important? The definition of pH, which is a very important way, very common way of thinking about acids and bases, goes like this. The pH is equal to the negative of the base 10 logarithm of H plus concentration. So here's an example. If H plus concentration is 1.2 times 10 to the negative 4th, what is pH? Well, pH would be the negative of the base 10 logarithm of that H plus concentration, 1.2 times 10 to the negative 4th. Now you can get a rough estimate here by looking at this exponent. It's going to be somewhere around 4. What is it exactly? If you use your calculator, you'll find out that it's 3.92 to 2 decimal places. In a neutral solution, we've already seen that the concentration of H plus is equal to 1.00 times 10 to the negative 7th, which is also the concentration of OH minus. But if I take the negative of the base 10 logarithm of 1.00 times 10 to the negative 7th, I don't even need a calculator to do this one. It's going to be the opposite of negative 7, which will just be 7. So in any neutral solution, including pure water, the pH is equal to 7. What about in an acidic solution? Well, in an acidic solution, the concentration of H plus is higher because many protons have been donated. So what would that mean? Let's take a look at an example where we compare H plus concentration with pure water. In water, concentration of H plus is 1.00 times 10 to the negative 7th. Let's just pick a number that's bigger than that. So here's our acid. Some random acid has an H plus concentration of 1.00 times 10 to the anything bigger than negative 7th. How about negative 5? That's larger. So the pH here, of course, is 7. What's the pH here? Well, it's the opposite of negative 5. pH is 5. So in an acidic solution, pH is going to be less than 7. How about in a basic solution? Well, in a basic solution, there's more OH minus present than there is H plus. We know in any aqueous solution, the concentration of H plus times the concentration of OH minus has to be 1 times 10 to the minus 14th. That number never changes. So if this number is getting bigger, it can only be because this number is getting smaller. So the H plus concentration has to be less than what it is in water. So in pure water, we saw already H plus concentration is 1.00 times 10 to the negative 7th, which leads us to a pH that is equal to 7. But in a base, the concentration of H plus has to be a smaller number than that. So let's pick any random number that's smaller than that, like 1 times 10 to the minus 9th would be a good example. Here the pH is 9. So in a basic solution, pH is bigger than 7. Because of the definition of H+, we can find H+ if we know what the pH is. Here's how we can work this out. By definition, pH is the negative of the base 10 logarithm of H+ concentration. If we want to know H+ concentration, we can solve for it. The first thing we can do is divide both sides by -1, and that would give us negative pH is equal to the base 10 logarithm of H+ concentration. From math classes, you might know that how you undo a logarithm is take the anti-log, which means to raise 10 to the number. So let's raise 10 to both sides. That gives us this. 10 to the negative pH is equal to 10 to the log of H+ concentration. But 10 to the log of something is just that something. So that's equal to H+ concentration. So now we have a formula that allows us to calculate H+ if we know pH. Like in this example. If the pH is 6.24, what's the H+ concentration? Well, the concentration of H+ here is going to be equal to 10 to the negative 6.24. And that's going to have 2 sig figs in it, because I have 2 decimal places in the pH, and that comes out to 5.8 times 10 to the negative 7th for H+ concentration. If the pH for a certain solution is 4.74, let's find out, first of all, what's H+ concentration, and then what's the OH- concentration. Stop the video and try this, and then I'll bring you the answer. Well, the concentration of H+ you can find easily enough by taking 10 and raising it to the negative pH, which in this case would be to the negative 4.74. That works out to 1.8 times 10 to the negative 5th. OH- concentration? Well, we've learned earlier that OH- concentration is equal to Kw divided by the H+ concentration, which we now know. So Kw is 1.00 times 10 to the negative 14th, and the H+ concentration is 1.8 times 10 to the negative 5th. So when we do our math here, we get 5.5 times 10 to the negative 10th as the OH- concentration. There's a related concept that isn't used as often, but it works the same way. pOH is the negative of the base 10 logarithm of concentration of OH-. Here's an example. For a lake, H+ is 3.2 times 10 to the negative 5th. Let's find the pH, and then let's find the pOH. And then let's ask ourselves, is the lake an acidic or basic solution? Well, since I know H+ concentration, I can find pH. pH is going to be equal to the negative of the base 10 logarithm of my H+ concentration, 3.2 times 10 to the negative 5th. That works out to 4.49. So there's pH. Now, pOH, I could find the OH- concentration and then take the negative base 10 logarithm of that, and I'd have pOH. But there's another way. If I take a look at the idea that the concentration of H+ times the concentration of OH- has to be equal to 1.00 times 10 to the negative 14th, if I take the negative of the log of both sides, here's what I get. Minus base 10 logarithm of H+ concentration times OH- concentration is equal to minus the base 10 logarithm of 1.00 times 10 to the negative 14th. Well, on the right-hand side, minus base 10 logarithm of 1 times 10 to the minus 14th is just 14.00. On the left-hand side, I could rewrite this as minus the base 10 logarithm of H+ concentration plus minus log of OH- concentration. But the log of H+ concentration, the negative of that, is pH. And the negative of log of OH- concentration is pOH. And that equals 14.00. So we can use this fact to shortcut this kind of a problem. So if I take 14.00 and I subtract the pH, 4.49, I will have the pOH value, which is 9.51. Is the lake acidic or basic? Well, we can look at the pH and quickly tell that it's below 7, so this is an acidic lake. Well, you'll have an opportunity to practice using pH and pOH. In our next video, we're going to use the idea of pH to track what's happening during changes that involve acids and bases.